Hey everyone, happy Wednesday. I have a whole lot of equations for us to solve today, but first I was wondering if we could take a look at doing this. If I tell you that log base 2 of 3 equals 1.584, can you get me a value for log base 2 of 24? And ideally, we don't use our calculators for this. Take a minute to think about how you could use your log properties in this problem to evaluate this log with this one piece of given information. How'd you do? Did you think to rewrite this as log base 2 of 8 times 3, which would be log base 2 of 8 plus log base 2 of 3? Hey, and wait a second. Log base 2 of 8 can be rewritten as 2 to the third. And then we can use our power property and then log base 2 of 2. Well, we said yesterday that that was 1. Log base b of b is always 1. So 3 times 1 plus log base 2 of 3, or 3 plus 1.584. But you might have thought to do this problem as log base 2 of 6 times 4, in which case you would have written log base 2 of 6 plus log base 2 of 4. And then you would have said, oh, 6, that can be broken down into log base 2 of 2 plus log base 2 of 3. And log base 2 of 4 could be log base 2 of 2 squared. We could use the power rule here and get log base 2 of 2 plus log base 2 of 3 plus 2 log base 2 of 2. And what I know is that log base b of b is 1. So I have 1 plus 1.585 plus 2 times 1, or 3 plus 1.585. In both cases, we get 4.58. Oops, 4. So you can break this up any way you want. Either way, you should get the same answer. Why don't you try one now? Will you do log base 2 of 12? And when we're done going over this, we'll start solving different types of equations. Five, 4, 3, 2, 1. Okay, did you write log base 2 of 4 times 3 and come up with log base 2 of 4 plus log base 2 of 3? Log base 2 of 4 is 2 squared. And we can use that power rule to bring the 2 down. Log base 2 of 2 is 1, so 2 times 1 plus 1.584 gives me 3.584. Okay, so that's worthy of our next test. You want to make sure you're comfortable doing problems like that. And now, let's start solving. That's the big topic today, solving. I want to solve exponential equations first. Here's the first one. 4 to the x equals 16. Well, we've seen this one a bunch now, and we know that what we need to do is rewrite so that we have the same base on each side. I can rewrite this as 4 to the second. That'll be nice. Or we could rewrite both sides with a base of 2. In this problem, 4 to the second is probably fine. 4 to the x equals 4 to the second. And then we can use our one-to-one property and say x equals 2. Or we could take the ln of both sides and bring down these powers and have x ln of 4 equals 2 ln of 4. And to get x by itself, I would divide by ln of 4. So x equals 2. I don't think I'd go to all this trouble of taking the log of both sides when I could just use the one-to-one property. So I'd stop there, I think, with the one-to-one property as 4 to the x equals 4 to the second. And since these terms are equal and their bases are the same, the exponents must also be the same. But we're going to see some problems today where it will be helpful to take the log of both sides. So I wanted to introduce that early on. Okay, can you do this one then? 3 to the x equals 243. 5, 4, 3, 2, 1. If we rewrite 243 as 3 to the 5th and then use the one-to-one property, we see that x should equal 5. How about something a little more challenging? How about something like 7 to the x equals 1 over 49? Give that one a try. Remember, you want to rewrite so that both sides have the same base if you can. 5, 4, 3, 2, 1. Well, so I'd probably think about doing this problem as 7 to the x equals 1 over 7 squared, or 7 to the negative 2. And since 7 to the x equals 7 to the negative 2, x equals negative 2. But you know, you could do this. You could take the log of both sides. 1 over 49. In fact, I want to take the log base 7 of both sides. Over here, I'm going to use my power rule. X log base 7 of 7 equals, a quotient. We can use our quotient property to write this as log base 7 of 1 minus log base 7 of 49. Well, we know log base 7 of 7 is 1, so we get x over there. Log base 7 of 1 is 0, and then over here, 49 is 7 squared, and so I can write this as log base 7 of 7 squared, and bring down that 2. So x equals negative 2 log base 7 of 7. Log base 7 of 7 is 1. 1 times negative 2 is negative 2. Wow! I could get the same answer by going a much longer path. Why show you that? Well, some of the problems that we're going to do, we won't be able to write both sides with the same base, and we'll have to take an approach like this. Okay? But that's coming up. How about this one? What can you do with this problem? 1/2 to the x equals 32. Remember, you want to write so that both sides have the same base. Well, I think about this one as 2 to the negative 1 raised to the x and 2 to the 5th. When I raise a power to a power, I'm supposed to multiply those powers, and so I get 2 to the negative x equals 2 to the 5th. With the 1-to-1 property, I know that negative x equals 5, and if I divide both sides by negative 1, x equals negative 5. Exponential equations are ought check. You don't have to must check these like you do log equations. Okay? So will you do this problem? Will you do 1/4 to the x equals 64? Five, 4, 3, 2, 1. Well, let's take a look. I thought about this as 4 to the negative 1 to the x. I thought about this as 4 to the 3rd. When I raise a power to a power, I multiply. And so negative x equals 3, which means positive x equals negative 3. It's okay to get a negative number is our answer here. All right, let's try something a little more challenging that's an exponential equation. Don't worry, Brian, it's still in our comfort zone. 9 to the x minus 1 equals 27. So I want to rewrite these so that they have the same base. This is 3 to the 2nd, this is 3 to the 3rd. So I'm going to write 3 to the 2nd raised to the x minus 1 equals 3 to the 3rd. Please remember, when you're raising a power to a power, you're multiplying. So I have to multiply that 2 times both the x and times the minus 1. This is going to be 3 to the 2x minus 2 equals 3 to the 3. Using the 1-to-1 property, since the bases are the same and the terms are equal, we can say that 2x minus 2 equals 3, or 2x equals 5, or x equals 5/2. Now will you try this one? 32 equals 4 to the 3x plus 1 power. Take a moment to do this one, and then after this, we'll start looking at dealing with some log equations. Five, 4, 3, 2, 1. Well, I see 32 could be written as 2 to the 5th, and 4 could be written as 2 squared. When I raise a power to a power, I multiply. Remember, that 2 has to be multiplied both to the 3x and to the 1. So on the left side, we still have 2 to the 5th, but on the right side, 2 times 3x is 6x, and 2 times 1 is 2. Now, since the bases are the same and the terms are equal, I know that 5 equals 6x plus 2, or 3 equals 6x, or x equals 1/2. Okay, remember exponential functions are ought checks, they're not must checks. If I really wanted to check this, I could always plug a number in up there, this number, into the original equation. 32 equals 4, 3 times 1/2 plus 1. 32 equals 4 to the 3/2 plus 1, which is 4 to the 5/2. Well, if I turn 4 into 2 squared, I end up with raising a power to a power, so I would multiply and those would cancel. And I'd have 2 to the 5th equals 32, or 32 equals 32. So that's all good. Okay, so I was thinking we would move on to log equations now, but I think actually I'd like to do a few more exponentials, but of a slightly different type. So, for example, what if I have 2 to the x equals 3? Well, I need to get this x down. And we said that there was a power property that in the presence of a log or an ln, we could bring this down with the power property. So I'm going to take the log of both sides. Log of both sides. And bring that x down. And now I have x log 2 equals log 3. This x is attached to the log 2 with multiplication, so if I want to get x by itself, I have to divide by log 2. So x equals log 3 over log 2. Please do not try and use the quotient property here. This is not two logs where you're now going to write them as one log with subtraction. Oh my goodness, I've seen students do that. There's no quotient property here. Nor also can I do that. No. I will definitely chase you with a stick if you do that. The answer here is log 3 over log 2. If you really want to know what that's equal to, pull out your calculator and do log 3, close parentheses, divided by log 2, close parentheses, hit enter. But don't cross this out and don't try and use the quotient rule here. Okay? How about this one? How about we have e to the x equals 4. Again, I want to try and get that exponent down. And instead of taking the log of both sides like I did over here, I think I'm going to take the ln of both sides. When I bring this x down, I get x ln of e equals ln of 4. Now, what's the ln of e? Ideally, from Friday, you remember that the ln of e is equal to 1. But if you're not sure about that, remember, ln of e is the same as log base e of e. And we said yesterday that log base e of e was 1. Okay, so we have 1 times x equals ln of 4, or x equals ln of 4. Will you try then solving this exponential equation? E to the x equals negative 3. Five, 4, 3, 2, 1. Okay. Did you take the ln of both sides? Did you bring this down with the power property and say that x ln e was the same as x times 1, or x? But look over here. we have the ln of negative 3. Can we take the log of a negative number? Nope. So this is no solution. We could think about that from the original problem. We could think about that from the original problem graphically. If we take a look at e to the x and at the line y equals negative 3, here's our e to the x graph passing through 0, 1, 1e, negative 1, 1 over e. When does this graph intersect the line y equals negative 3? That's what I see when I see this equation. I see this equation saying, when does this graph intersect this line? Well, this graph never intersects that line. There's no point of intersection, and we're able to see that over here algebraically when we're trying to take the ln of a negative. Remember, you can't take the ln of a negative or of 0. Okay, let's move on. Let's deal with some log equations. And I'd like to think that we have some strategies here as well. The one-to-one property might be good, condensing might be important here, and exponentiating will be important. So let's look at first at some basic condensing problems. For example, ln of x minus ln of 2 equals 0. Okay, so I can do this problem a couple of different ways. The first, if I'm using condensing, is to think about doing this problem. Aha, 2 logs joined with subtraction, we said yesterday, meant we could use the quotient property to rewrite this as ln of x over 2 equals 0. Now, I want to exponentiate both sides here. Remember that verb from yesterday, exponentiate. Exponentiating is what I do when I want to get rid of that log. It's not log times this, so I'm not going to divide by the letters ln. I will look sad at you if you try and do that. Instead, in order to undo taking the ln, I need to exponentiate with e, because ln is log base e. If this said log base 2 of x over 2, I'd exponentiate with 2 on both sides. And if this said log base 7 of x over 2, I would exponentiate with 7 on both sides. But it does say log base e or ln, so I'm going to use e as the base on both sides. Now on the left-hand side, e to the power of and log base e cancel each other out, and we're left with x over 2. On the right-hand side, e to the 0 is 1, and so I end up with x equal to 2. Remember, log equations are must check. It's not did I get a negative number, it's not did I get 0, it's what happens when I plug that back in there. So ln of 2 minus ln of 2, no problems, I get 0 equals 0. There are, of course, other ways to solve this equation, but we were told to solve it with condensing. If they didn't tell us to solve with condensing and just gave us ln of x minus ln of 2 equals 0, we might add ln of 2 both sides. And then you could use the one-to-one property, saying that if these things are equal and they are both ln's, then the stuff inside must be equal as well, so x would equal 2. Or you could exponentiate both sides. And you could say e to the ln cancels, e to the ln cancels, and you get x equals 2. So those are other ways of solving the same problem, but the directions were to solve by condensing, and so I wanted to show my mastery of the log properties here and apply those. Will you solve this one by condensing then? ln of x plus ln of 5 equals 0. Try your hand at solving that, and in a few moments we'll have a countdown and take a look at how to do this problem. Five, 4, 3, 2, 1. Okay, so with our product property, we can rewrite this as 5x. Then, to get rid of this ln, I can exponentiate. These undo each other, and so I have 5x equals e to the 0. E to the 0 is 1, and so if I want to get x by itself, I'm going to have to divide both sides by 5 to get x equals 1/5. Remember, this is a must-check situation. It's a log equation. Any equation that has logs in it, I've got to go back and check. Is it a problem to plug in a 1/5 there? No, this number is not going to give me a 0 or a negative number to take the log of. And some of you may be wondering, well, how does this turn out to be 0? Well, if you rewrite this as ln of 5 to the negative 1, and then use that power property, you can see negative ln of 5, positive ln of 5 would be 0. Okay? All right, let's take a look at some other ln equations. I'm looking now at ln of x equals -1. How can I solve this? Well, the only way I have to solve this is by exponentiating. It would help if I spelled the verb correctly. Exponentiating. So I want to use the log base. In this case, this is log base e, so I'm going to use e as the base on both sides. Over here, e to the ln cancels, leaving me with x. I get e to the -1, or 1 over e. Can we plug that back in there? Well, ln of e to the -1, I use that power rule, -1 ln of e. We should know by now that the ln of e is 1. So -1 times 1 is -1. And that's what we were supposed to get. Remember, log equations are must checks. You want to make sure when you plug that number in that you're not asking ln to take the log of a negative number or 0. Okay? So will you try this one? ln of x equals 8. Five, 4, I know the countdown is fast, 3, 2, but there's not much to do here. All we have to do in this problem is to exponentiate. So I exponentiate here, and I get x equals e to the 8th. If you're curious to know how big a number that is, pull out your calculator and ask it about e to the 8th. It's a pretty big number. But I'm not interested in that. I'm interested in this next problem. Instead of an ln, log base 4 of x equals 3. Okay, I can think of doing this problem 2 different ways. What can you think of? Okay, who thought about today's stuff where we would exponentiate with 4 on both sides? 4 to the power of log base 4, those are inverses and undo each other, leaving me with x equals 4 to the third, or x equals 64. But if we go back to last week, when we see log base 4 of x equals 3, we could also think about doing this problem with scorpion tail. 4 to the 3 equals x, or 64 equals x. So we have two ways of doing this problem. Okay? All right, let's move on. I'd like to look at some other equations, in particular ones where you'll want to use or think about using the one-to-one property. So, for example, how about log base 3 of x plus 4 equals log base 3 of 1 minus x. So we can do this problem in one of two ways. We can use the one-to-one property, and since we see these terms are equal and they're both log base 3's, we know that their arguments need to be equal. So that x plus 4 should equal 1 minus x. But if you've been thinking about exponentiating a lot today, you might also think to say, well, I'm going to exponentiate with 3 on both sides. 3 raised to the power of log base 3, these will cancel on both sides, leaving me x plus 4 and x minus 1. If I add x to both sides and subtract 4 from both sides, I get 2x equals negative 3, or x equals negative 3 halves. Now, it's not that x is negative that automatically means I should throw this value away. This is a must-check situation. What happens when we plug this negative 3 halves into both of these terms? Well, on the left-hand side, I've got log base 3 of negative 3 halves plus 4. 4 is 8 halves. And on the right-hand side, I have log base 3 of 1 minus a minus 3 halves. Well, 1 is the same as 2 halves. So on the left-hand side, I've got log base 3 of 5 halves. And on the right-hand side, 2 minus a minus 3 is 2 plus 3. And so I'm going to have log base 3 of 5 halves over here. Please note, I'm not taking the log of a negative. I'm not taking the log of 0. So this answer, x equals negative 3 halves, is fine. It's perfect. It's only if we have a negative here or here, if we have a 0 here or here, that we're in trouble and we need to say no solution, or at least this wouldn't be a solution. But in this case, this must-check situation with logs, this answer, x equals negative 3 halves, works just fine. Okay, let's do another one. How about this one? You can try this one. Log base 5 of x minus 2 equals log base 5 of 3x plus 7. I don't care if you exponentiate or use the one-to-one property here. I would like you to solve this equation for x. Okay, let's see how it went. I exponentiate on both sides. I get x minus 2 equals 3x plus 7. I subtracted x from both sides. I subtracted 7 from both sides. I get negative 9 equals 2x. And x equals negative 9 halves. Now, when I take that negative 9 halves and plug back in, I see on the left-hand side Negative 9 halves minus 4 halves is going to be log base 5 of negative 13 halves. Can I take the log of a negative number? No. So since this was my only solution, I have to say here, no solution. Okay? Now, when we think about this, I like to think that graphically this will make sense. One of our equations was log base 5 of 3x plus 7. And so over here at negative 7/3, we'd have a vertical asymptote. And then the other equation was log base 5 of x minus 2, which would look like this. And so we're saying, when do these two curves intersect? And the answer is they're not gonna intersect. So it doesn't surprise me that here we've got no solution. So it may help me to think about these problems graphically. I also want to remember that I can't take the log of a negative number. It's not that x is a negative number that's a problem, as we saw in the last case, the problem we did, but that when we plug that negative back in and it doesn't work, i.e. we're getting a negative here or a 0 here, that's what we can't take the log of. And it doesn't have to happen on both sides of the equation. If it happens on one side or the other side that we get the log of a negative, then we want to say, no, we're not going any further here. Okay, will you try this one? Log base 7 of x minus 5 equals log base 7 of 6x. Try that one. Okay. 5, 4, 3, 2, 1. If I exponentiate here with 7, these cancel and these cancel, leaving the x minus 5 equals 6x. If I subtract x from both sides, I get negative 5 equals 5x. And if I divide by 5, I get x equals negative 1. Is that good? No, because when we plug that negative 1 back in here, or in here, in either case in this problem, we'd have log base 7 of negative 6. And while it's true that log base 7 of negative 6 is equal to log base 7 of negative 6, I can't take the log of a negative, and so this is no solution. Okay? So watch out for no solutions. Log equations are always must checks. Okay? How about this one? Log of x squared equals log of negative 3x minus 2. Please solve this equation. 5, 4, 3, 2. I'm interested to know how many solutions you got in this problem. 1. I think there's 2. So if I exponentiate with 10 on both sides, I end up with x squared equals negative 3x minus 2. And because this is a quadratic, I want to move everything onto one side of the equation. So I'm going to add 3x and add 2 to both sides of the equation. And that'll give me x squared plus 3x plus 2 equals 0. Well, this quadratic factors as x plus 2, x plus 1 equals 0. And when I set each of these factors equal to 0, I get x equals negative 1 and x equals negative 2. And I'm tempted to say, oh, well, these aren't going to work because these are negative numbers. But let's see what happens when we plug them into the original equation. Log of negative 1 squared, because that's what we have here, x squared, equals log of negative 3 times negative 1 minus 2. Okay, so over here we have log of 1, which is 0, and over here we have log of 3 minus 2, which is log of 1, which is 0. 0 equals 0, and so we're good to go. And what happens when we plug in x equals negative 2? Well, we're going to have log of negative 2 squared equals log of negative 3 times negative 2 minus 2. That'll be log of 4 on the left-hand side, and on the right-hand side, log of 6 minus 2. Log of 4 equals log of 4. Both of these are positive numbers. We're not asking log to take the log of 0 or negative, so I think not only does negative 2 work, but also negative 1. We've got 2 solutions here, okay? All right, let's take a look then at this last type of solving. This is a little more algebraically intense. This is solving a logistic equation. We haven't graphed any logistic equations, and hopefully we'll see some before the end of this chapter. Logistic equations start off like exponential growth, but then instead of just having one horizontal asymptote, they have a second one, and they have to bend to that one as well. So this S shape is a logistic curve, and the equation for this looks something like this. 501 plus 3e to the negative 0.4x. And I'm wondering when this equals 200. Well, the first thing I want to do, oh, hey, see this negative exponent? You can't flip that up because all of this is tied to this with this plus sign. And this negative exponent doesn't go for all of this stuff, it just goes for that. So those of you contemplating this negative exponent and doing a flippy kind of thing, you would have to write this. And that is not something I recommend doing. Okay? You can flip this down if you really want, but you definitely can't flip it up because this is tied to those other objects. Okay? Instead, we're going to treat this problem just like this. Where I have a denominator in an equation, and what I do is I multiply both sides by that denominator to clear that denominator out. Which means in our problem, I'm going to be multiplying both sides by 1 plus 3e to the negative 0.4x. 1 plus 3e to the negative 0.4x. Now on the left-hand side, this cancels that, leaving me 500. And on the right-hand side, I have 200, 1 plus 3e to the negative 0.4x. Now, some students at this point like to distribute. I do not like to distribute. You should still get the same answer, but you're going to be dealing with bigger numbers than I am, because what I'd like to do is, since this is attached to this with multiplication, I'm going to divide both sides by 200. And now I have all that stuff by itself. And over here, I can do some canceling. So 5 halves equals 1 plus 3e to the negative 0.4x. Okay, what would we do next? Well, SADMEP says subtract that 1. 3 halves equals 3e to the negative 0.4x. Well, I know I'm going to have to take the log or ln of both sides to bring this power down to solve for that x. But before I can do that, I need to get rid of this 3. This 3 is attached to this stuff with multiplication, so I'm going to divide both sides by 3. Okay, what does that leave me? 3 halves divided by 3. Well, if we do flip and multiply, 3 halves divided by 3 becomes 3 halves times 1 over 3. And on the other side of the equation, we have e to the negative 0.4x. These cancel, leaving me 1 half equals e to the negative 0.4x. And then I want to take the ln of both sides. Remember, if I take the ln of both sides, I can use my power rule to bring down this power. So I get the ln of 1 half over here, and over here we've got negative 0.4x ln of e. What was the ln of e again from earlier? We said the ln of e was negative 1. I'm sorry, positive 1. So now I'm looking at this. In order to get this x by itself, I need to get rid of the negative 0.4 times x. So I'm going to divide by negative 0.4. These will cancel, and x will be ln of 1 half over negative 0.4. Now it is possible for us to go a little further with this, but generally speaking I would stop here. You might want to rewrite this as ln of 2 to the negative 1, and then use that power rule over negative 0.4, and then this negative and this negative will cancel. And so you'll end up with ln of 2 over 0.4, or 2/5, or 5 ln of 2 over 2. No, you can't cancel those out. So I wouldn't mark this wrong on a test. I would put this down as a multiple choice answer, okay? All right, so now let's go over this again. What did we do at the beginning? We saw this equation and we said, logistic, but don't be scared. We multiplied both sides by the denominator to cancel the fraction denominator on the left. On the right, instead of distributing, we divided both sides by this 200 to get the stuff in parentheses alone. And then we did some SADMEP. We subtracted 1 from both sides and divided both sides by this 3. That gave us this 1 half equals e to the negative 0.4x. In order to bring this x stuff down, we needed to take the ln, or log, of both sides. So now I've got ln of a half on the left, negative 0.4x on the right, and I know that ln of e is 1. If I divide both sides by negative 0.4, I get my answer. Logistics are ought check. So you don't have to must check these. We can tell by the graph that there's no restriction on this domain. Any x value will work. Okay, so now it's your turn. Here's your logistic equation to solve. 1,000, 1 plus 2e to the negative 0.5x equals 100. Okay. Please take a couple minutes to solve this one. In fact, I think I'll do it on the board while you do that one. I'll do it on the other board. Actually, I'll spill a lot of water all over the place and clean that up first, because some of it's running into the document camera. If you hear a loud buzzing, it's probably me being electrocuted. This is good. I can be cleaning up water while you're doing that terribly long problem. There's a lot of water. How are you doing on that problem? I'm almost done with the water spill, so we will get together in a moment and see about solving that logistic. Okay, well, I've cleaned up the mess, so you should be done with that problem by now. I'm going to have to play catch up because I haven't started it yet. Okay, let's take a look. I see here that if I multiply both sides by 1 plus 2 e to the negative 0.5x, 1 plus 2 e to the negative 0.5x, I can cancel out the denominator. I'll have 1,000 equals 100, 1 plus 2 e to the negative 0.5x. Yes, you can distribute, but I'm not going to. I'm going to divide both sides by 100, and I'm going to get 10 equals 1 plus 2 e to the negative 0.5x. I'm going to subtract 1 from both sides. I'll get 9 equals 2 e to the negative 0.5x. I'll divide both sides by 2. And now we have to take the ln of both sides and use our power rule to bring this down. ln of 9/2 equals negative 0.5x ln of e. Remember, we've said a number of times now that ln of e is 1. And so we're really just looking at this. To get x by itself, I'm going to divide by negative 0.5. And I'm going to get x equals ln of 9/2 over negative 0.5. If you want to use your log properties to rewrite this as ln of 9 minus ln of 2 over negative 0.5, you can. You can even break this down into 2 ln of 3 using your power property. But I really don't find the need to do that. You can if you like. In fact, you could even turn this into dividing by negative 1/2 as being 2 ln of 2 minus 4 ln of 3. So if you're going to go the simplifying route, this is what you'd see in a multiple choice answer, but this would be fine on our test. Okay? All right. So that's solving equations. Do we have any time left? We have a couple of minutes. Let's see if we can squeeze in one or two solving problems. And I'm not going to tell you how, I'm just going to say solve. So how about this one? E to the x ln of 3 equals 27. How will we solve that? Five, 4, 3, 2, 1. Well, I hope you said you would take the ln of both sides, so you could use the power rule to bring this down. This will be x ln of 3 times ln of e equals ln of 27. Hey, isn't 27 3 to the third? So over here on the right-hand side, I could use the power rule and get this. And on the left-hand side, ln of e is 1. And so I have x ln of e. If I divide both sides by ln of 3, I get x equals 3. Huh, wow, did you see that coming? You know, there's another way to think about doing this problem. It takes a little more perception, sometimes very hard for people to see. But if we start off with the original equation, x ln 3 equals 27, and we think about using the power rule in this exponential power. And so we rewrite this as e to the ln of 3 to the x equals 27. E to the power of log base e, these cancel, and we're left with 3 to the x equals 3 to the third, and so x equals 3. So we have a couple of ways of doing a problem like this. Okay, well, I think we're going to call it quits here because it looks like 57 minutes, and that means if the bell hasn't rung already, the bell is about to ring. I hope you have a wonderful afternoon, and I will see you tomorrow. All right, take care, and don't forget to send me your questions. Bye-bye.